Oh, yeah, it is. So, first, yesterday and the day before, we talked about the most basic building block of energy starts here. That motion is energy, and it is the most basic form of energy that there is. Although it has wide-ranging implications, the most important part about knowing that any motion is a reference to energy is the fact that it's very visual and it's very obvious and it's very measurable. So the concept of kinetic energy is very much fundamental to our understanding of energy as a whole. But yesterday also we talked about the difference between net work, which we know is equal to the change in kinetic energy, and work done by a fundamental force or an individual force as an integral or as an algebraic when we have a constantly applied force. That this represents the work done by individual forces, but if I add them all up, that would be the net work. And let me be quite direct here. The word net is something that really needs to, be in your vocabulary, in that net is small, but it changes the meaning of what we're talking about dramatically. So when they ask for net force, they're specifically asking you to take a look at the acceleration. When they're asking for net work, they're specifically talking about the change in kinetic energy. Although there are other ways to calculate it, if you can find the acceleration or if you can find the kinetic energy, that will always be the most direct route in calculating net force and net work. Now, we also talked yesterday about the work done by a spring as minus 1/2 k x squared. And I don't mean to be difficult about the minus signs here, but I need you to kind of understand something, that minus signs have big implications, especially when we're talking about broad understanding of a concept. Hooke's law has a minus sign in it. And although that minus sign seems minor, the minus sign signifies that this is a restoring force, that any object that obeys Hooke's law, when it is in any way displaced from the origin, there immediately springs into action a force to attempt to return it to its original position. That minus sign has big implications. I want you to imagine a way of expressing the difference between a minus and a plus. Consider a shallow bowl. The equilibrium position is at the bottom of the bowl. If I put a marble here, that would be equilibrium. If I take and slide the marble up onto the side of the bowl, there will immediately be a restoring force that will attempt to return the marble back to the bottom of the bowl. This traps the marble in the bowl, but it also means that any attempt to deviate the marble from equilibrium is met with a return force that tries to return the system to equilibrium. That doesn't seem like much, but if we take the same bowl and turn it over, this bowl still has an equilibrium position. I can place the marble right here in its equilibrium position. But now if I attempt to move the marble a small amount, will there be a restoring force attempting to return the marble back to its original position? I mean, all we're talking about is one change of a sign. But in this case, the force is in the direction of the displacement and will act to move the object away from equilibrium. Now look, we don't design our buildings like this. This would be a building where if the wind hit the building, there'd be a force to push the building over. We design our buildings like this. The wind hits the building, there's a force to return the building back to the upright position. So here in Florida, it's wind mitigation. In California, it's earthquake mitigation. There's going to be displacements to the building. We're going to try and mitigate those circumstances by creating the conditions for stable equilibriums. That's what these two things suggest. This system can have unstable equilibriums, but by placing or working on a system that has restoring forces, we are creating stable equilibriums. So I don't want you to think that this is me just trying to be, critical or mean. There are big, wide implications in dealing with something as small as a minus sign. And I don't want to just throw it away. The minus sign here indicates that the work being done to compress the spring has to come from somewhere else in order to get the spring compressed. Meaning the spring does work against the environment. to store the energy in the spring. We might be able to get that energy back, but in the meantime, the energy is in the system of the spring. So I want to stay on that for just a minute to talk a little bit about the energy stored in the spring and to introduce the concept of potential energy. So first, let's just use the idea of a classic ideal Hooke's law spring. So here we have a spring in its relaxed condition, this representing equilibrium of 0. Box of mass m, spring constant k. All right. Now, let's say through some interaction, I'll try and be careful here, draw it nice and neat. Let's say through some interaction, the spring has become compressed and the box has changed positions so that now there is a clear displacement of the spring. Now, the first thing I need you to understand here is that work was done by the spring on the box, and it was negative. It's negative for a really easy reason. The box was displaced to the right, but the force from the spring was to the left. Even though we had to do this from the standpoint of an integral, it should be clear that the cosine between the displacement and the force from the spring is the cosine of 180 degrees. That's got to be -1. Now, what's interesting is that unlike friction, which takes energy away, in this case, if I release the box, the spring can immediately do positive work on the box, accelerating the box the way it came. So although the work by a spring is essentially negative, that energy isn't lost. That energy is stored in the interaction between the box, the spring, and whatever the spring is connected to. It's important to understand that there has to be a system here. We can't just push on a spring, in a room and assume that the spring is going to store energy. If I push on the spring under this circumstance, will the spring ever compress? There's no background there. There's nothing for the spring to hold on to, nothing to apply a force to the spring on the other side. There is no interaction, and all I get is the spring is now over here. We have to be very clear that this form of work requires the interaction between two or more objects in order for that energy to stay stored within the system. What I mean is that potential energy is a storage of energy through the interaction of two or more objects. That's the definition of potential energy. In AP Physics 1, we would just talk about potential energy as this quantity that you have. But we need to change our understanding a little bit to understand that potential energy is an interaction, meaning it exists because of the interaction of two or more objects. Here, it's the interaction between the block, the spring, and the backboard that holds that spring in place. Without all of those things there can be no storage of this energy. But if there's a reciprocation, if there's the ability of the system to reciprocate back to its original condition, we say that potential energy can be stored. And we say that potential energy is the opposite of the amount of work done on the interaction on the system. Kind of stumbled over that again. So I'll say we define potential energy as the negative amount of work done on a system where there's an interaction. Still stumbled pretty badly on that. So potential energy is equal to negative amount of work. Just leave it there. The implication here is that there has to be some kind of reciprocated system. Generally, what we're looking for is we're looking for a conservative force. Conservative forces allow you to retain the work that has been done on them. Friction is a non-conservative force. Once work has been done by friction, that energy can't be reciprocated. But a spring is a conservative force. All of the fundamental forces are conservative forces. There's not a lot of conservative forces out there, maybe a handful, but we'll talk specifically about energy storage in 3 or 4 different places. And the first one that we have right here is elastic potential energy. And that's going to be 1/2 kx squared. Now, I know you guys from last year know a little bit about this, but the details here is that potential energy is stored. It's a 1-for-1 interaction. For every joule of energy we put into a conservative force, we can get that joule back. There's not too many systems that allow for perfect reciprocation of energy, but all conservative forms of force will give you reciprocation of the energy. I'm not sure if that's coming through great, so let me try this. Consider a box. Okay, I'm going to lift the box from the ground a height h. Now, I want to focus on work for this discussion. And so to lift the box, I have to apply a force upwards. Now, I'm not exactly sure what's going to happen to the box, but I am confident that the work I would have to do to lift the box would have to be equal to the amount of force I apply times the cosine of 0 degrees. I lift up on the box and the box does go up, times how high I lift the box. This is the amount of work I do on the box. Fair enough so far? No big deal. But while I'm doing work on the box, there's certainly going to be a gravitational force acting on the box at the same time. Now, it doesn't matter whether the force I apply is greater than, equal to, or less than the weight. Although I don't think I can lift the box if I don't apply a force that's at least as equal to the weight. It doesn't matter though. The amount of work done isn't based on the size of the force, just how much work is being done. So in the case of this example, the work done by gravity is going to be equal to mg times cosine of 180 degrees times h. Now, this inherently is a positive number, while this inherently is a negative number, because I'm doing work against the gravitational force. Gravity's acting down, but the object is moving up. So the net work being done will be the difference between these two. Now, there's several possible implications here. The most likely is I push up harder than the box actually needs, and the box has a change in kinetic energy, meaning it makes it to this level, but it now has velocity because I pushed up with more force than was necessary. So it doesn't stop here. It continues to go up because the box now has kinetic energy at this point. Of course, it is also possible that I could apply a force that is equal to the weight of the box. If I do that, then likely this sum is going to be 0. That doesn't mean the box doesn't move. It just means that when the box gets here, it doesn't have a change in its velocity. Now, you might not buy into this next one, but it's also possible that I could apply a force that is less than the force of gravity. It'd be unlikely I'd make the box go upwards under this force, but I could imagine that the box is falling downwards and I apply an upward force so that it doesn't have too large a change in kinetic energy. Have you ever tried to stop something from hitting the ground, or at least not hitting the ground too hard? You would do so by trying to break its fall. And that's what that would be, doing a little bit of work on it so that its kinetic energy doesn't change too dramatically. Either way, when we talk about the work, positive and negative work are just implications of direction of force. Their ability to leave you with energy just represents that when work is done on a system, any residual amount of work that's left over goes into the kinetic energy of the object. I can imagine a problem on a ramp where an applied force, the weight of the object, and friction all contribute to whatever's going to be the change in kinetic energy of the object. Now, what I'd like to do is show you how in practice we tend to see this on the AP exam, but not without at least making sure that you see that working against gravity produces this negative amount of work, suggesting that there is a gravitational potential energy. That's going to be equal to mg. I'm going to write it a little different than what I wrote up there. H minus H naught. Potential energy is opposite of the amount of work done against that force. So since U is equal to minus W, this is the amount of work done by that conservative force. This is my expression for potential energy. Now, anybody who had physics last year knows why it's H minus H naught. But for those of you who don't, H naught represents what we call the reference level. When we change our height relative to a reference level. Now, you need to make sure you understand though. Last year, I wouldn't have been as clear about this. Potential energy is not something an object has, although colloquially we'll say the object has potential energy when it's here. What we really mean to say is that the interaction between the object and the earth gives the system potential energy. That's how we're supposed to say it. That's a lot more words. But when you're answering an AP question and they ask for you to explain yourself, those are the words you should use. That the object doesn't have potential energy, but the interaction between the object and the earth yields potential energy. So the more we attempt to separate an object from the earth, the more potential energy we store in that system. That's what this is saying. So let's consider this scenario. I have a spring that's relaxed position is a height h1 above the ground. And there's a box located a height h2 above the ground. There. I guess you can probably see that better now. There. Now, what I'd like you to think about here for this example is, can you come up with an expression for how fast the object would be going when it makes it to point A in this diagram? I'm hoping that all of you can. This is relatively straightforward. And in this case, gravity is going to do positive work on the box. So in considering the work done by gravity, I would note that gravity would apply a downward force, mg, the box would be pulled downwards, so cosine of 0 degrees. And the amount of work done by gravity would be based on the fact that it travels a displacement of h2 minus h1. That gets the box right to here. There, right to there. But this is a positive amount of work. So the net work being non-zero means that this is going to equal the change in kinetic energy, which is how we would figure out how fast the box is moving. Now, what I want you to do instead is consider this. Could you, using what's been given here, figure out how far the spring is compressed when the box hits the spring? Meaning the box, if allowed to pass point A, is going to apply a force to the spring that's going to have the result there of compressing the spring, say, some distance x. Can you come up with an expression for how far the spring is compressed? Give it a shot. Take a few seconds, see if you can. Now, I know what you're probably all thinking about doing, but I'd really like you to consider this from the standpoint of work and energy and not conservation of energy. Meaning, the box travels a distance until it comes to rest against the spring, which tells me that the change in kinetic energy is 0. The net work on the system is 0. Gravity is going to do positive work, but the spring is going to do negative work. I know the net work has to be 0 because the object starts with a velocity of 0 and ends with a velocity of 0. So the change in kinetic energy is 0. Now, that being said, the work done by the spring, well, that's easy. Negative 1/2 kx squared. I really don't have to do all the fancy math and integrals to know that. The work done by gravity, well, do you have an expression for how far the box traveled? Shouldn't be tough, right? Here to here is h2 minus h1. It then travels an additional distance x as it compresses the spring. Gravity is still acting downwards on the box right here when it hits the spring, and gravity will continue to act downwards on the box while it's compressing the spring. So gravity does work the whole time. That's because this is actually the reference level. It's the lowest point attained by the box. That's our reference level for gravity. I mean, in this problem, what we've actually been doing is using this as our reference level. All heights were measured from that except for x. Now, I'm bringing this up because if you're really paying close attention, and Matt should be, because I'm about to ask him a question, mg times h2 minus h1 plus x minus 1/2 k x squared equals 0. Is it clear to you why this is weird? It might not be because it's Friday and you are minutes away from being able to be told to not worry about physics, especially considering that, right now, This might be the only class you've had today. But that's a quadratic, which means there has to be two places where this is 0. Why 2?
Do I have to answer this one?
You don't have to, unless you know the reason.
Could I answer?
But I'll be happy to take anybody's answer.
Is it because when after the work by gravity, well, I mean, gravity's work is done, but when the spring comes back up and it can't like, and I forgot the term, but when the spring comes all the way back up and it can't like, it can't stretch anymore. Is that also like why there's 2 points?
Well, I'm not sure that you're doing a perfect job of explaining it, but it's right in there. Yeah. If the box were to stick to the spring, then the box would come back up and be pulled to a point where it would stop again, say up here, because the box would actually oscillate back and forth. This anticipates this idea that the box could have another location where the spring could do negative work on the box to take away any kinetic energy it has and stop it. And yeah, it would probably be up here, but it would have to get attached to the spring in order for that to happen. But this is why there's 2 values for X. Now, it wouldn't make any sense to think about that one on the first trip down. It would only make sense to think about that one if the box could interact with the spring in such a way that it would stick to the spring. But that is why there's 2 answers. The mathematics anticipates that, especially since, if you've noticed, X was squared here. The spring can be displaced in a negative direction, but energy isn't about direction, which is why any value that has direction in energy gets squared. 1/2 mv squared, 1/2 kx squared. Now I'm going to ask you one more question and then we're done. And this one I need a participation in the participant window. When I drop the box is going to be getting faster and faster and faster. In all of this, we talked about potentially where the box is going to stop. Does A represent the point where the box is traveling the fastest? If you think I'm right, if you think that's true, then put yes in the participant window. If you think no, then put no in the participant window. But does A represent the spot where the box is traveling the fastest? Got 3 people still waiting on. That's a lot of yeses. So this will be the first class where nobody caught it. No, it's not. And I think this is really worth paying attention to. The moment the box touches the spring right here, gravity has a downward force acting on it. But is the spring in any way compressed yet? So there is no upward force from the spring yet, which means the net force on the spring is still MA and is still downwards, which means the box is going to still be getting faster. Now, when the box moves down a little bit, say there, moves down a little bit. The moment it moves down a little bit, although that does not affect the gravitational force, it does affect the force from the spring. And suddenly there's a small force from the spring upwards. But this is still unbalanced downwards, which means the box is going to start to compress the spring and will still be getting faster until the point where the spring has been compressed enough for the upwards force to equal the downwards force. Meaning the box continues to get faster until the net force equals 0. Remember, what I said in class was that work is really good at talking about velocities and distances, but not so much in talking about accelerations. Because of that, if we want to know when the box stops accelerating downwards, we're going to have to downshift into force in order to deal with the acceleration. Now, this can tell us where the box is when it's no longer accelerating. And that will tell us when it's traveling the fastest. So now you guys who are veterans from being in physics last year, that's the kind of stuff that the AP exam is going to throw at you. You guys who are new to this, focus on the book work. Focus on the stuff that's in the book. But you guys who have done a little bit of physics already, when I put this problem up there, take a look at this one. This one does this kind of stuff to you. It makes you have to think through what's really happening. You can't just use energy and you can't just use force. You're going to be using a combination of both. Well, that's it for today. I'm not going to make you guys stay any longer unless you guys have a question or two you want to ask me. I had a feeling. Look, you guys, I do appreciate you guys taking the hard road and being here today. You know, I can't make it, you know, I can't tell you how much it means to me, but I can tell you that, you know, I don't want to feel like I'm the jerk holding class. I want to feel like the person who turned you guys loose on the holidays when I think it really matters most, not the special day that just happened to show up because there's a little bit of rain. So I'm glad you guys stuck it out. I'm glad you guys were here. And I look forward to seeing you guys on Monday. All right. Have a fantastic weekend. It's been real fun. And I'll see you guys on the flip side.
Bye, Mr. Shelton.
Bye-bye, guys.